Now in this experiment, we can approximate the binomial distribution by looking at the normal distribution. And that's because we are rolling a die 480 times and we're recording the proportion of rolls that are sixes. So before we go any further, what proportion of the rolls are you expecting to be sixes? About a sixth of them, right? And if there's 480, then a sixth of that would be around about 80 of them. Now the experiment is carried out many times. So here we're finding the probability of certain things happening when we keep on repeating the experiment. Find the probability that 1/8 or less of the rolls are sixes. Now I'm going to do this two ways. Let's do it using the methods that we learned in the last exercise, which doesn't involve using the proportion at all. It just involves using the number of outcomes, x. Then we'll do it using the proportion, and you'll be able to see that there's two ways that we can tackle a problem like this. In fact, there's three ways if we consider that our old methods we could either correct for the fact that our discrete data is not continuous, or we could perhaps not correct for it. Now, in the last exercise, I told you to correct for that, but we just want to have a look at what happens if you don't, because I think that's quite interesting here. Okay, so if we're letting x be the number of sixes, then the expected value of x, what are we expecting? Well, we find that by saying it's just n times p. So that's just 480 times 1/6. We're expecting 86s. And the standard deviation for x, well, we know that the formula for that is the square root of npq. So in this case, that will be the square root of 480 times 1/6, so that's 80, times 5/6. Now that gives us the square root of 66 2/3, which is roughly equal to 8.16, say. So let's store that as A. Now, if I'm saying that I want to find the probability that 1/8 or less of the rolls are sixes, then I'm finding the probability that x, which is the number of sixes I'm going to get, is less than or equal to 1/8 of that, which is 60. So I need to convert this now to a z-score and say, well, that's the same as the probability that z is less than or equal to something. So I'm wanting to find 60 as a z-score. So I say, all right, well, 60, it's below the mean. How far? It's 20 below the mean. How many standard deviations is that? I'm thinking sort of 2.5-ish. To get it exact, let's go 20 divided by our stored, 20 divided by our stored A. And we get 2.45 to 2 decimal places, but remember this is a negative z-score because our score is below the mean and it's 2.5 or so z-scores below the mean. And I've rounded this to 2 decimal places because my z-score table is rounded to 2 decimal places. So now I can look at my z-score table and see that the probability of being less than actually 2.45, because it doesn't have any negative scores on there, is going to be really high. It's 0.9, where is it? 9929. So that means the probability of being less than the negative of 2.45, this z-score, I want this little tail here, which is going to be the same size as this little tail up here. So I need to do 1 minus that, which is going to give me 0.0071. So very, very unlikely that I'm going to get less than 1/8. Now, you'll notice that I haven't corrected with that continuity correction. I haven't corrected for the fact that this was discrete data and I'm approximating it with continuous data. So this is with no correction. And we did this just as a comparison, because if we perform the same thing with the correction, now how do you work out what goes here? Well, consider what happens when you graph all of the number of sixes that you might get. You're rolling this die 480 times, so everything between 0 and 486 is possible. Obviously we're expecting something around here, around about 80, so this is the most likely, but you're going to have a column for every single thing that could happen. And the columns are going to look something like this. I mean, I'm just sort of roughing it out here. We're going to have a heap of columns, and they're going to get smaller this way and smaller that way. Now, we can make a polygon by joining up the tops of those columns. So if I'm considering that I want x to be 60, or less. Well, the column with 60 on it is here. And so if I just draw a line through the middle of that column, I've actually missed half of the column that's 60 itself. So actually, to get everything that's to the left of the 60 and include the whole of the 60 column itself, I would need to correct for it by doing 60.5. Now that's going to change my z-score ever so slightly, because if I say, well, how far is 60.5 below the mean? I can do 80 minus 60.5 to see how far it is below, divide that by my standard deviation, and I'm going to see that it's a z-score of negative 2.39, also rounded to 2 decimal places. So now looking at my z-score table again, obviously it's going to be 1 minus whatever I find on my z-score table. 2.39 is 0.9916. So that's going to make it just slightly more likely here, 0.00, what I have 84. And this is with the continuity correction. Now, I've told you that it's more correct to use this correction, and it is because we're approximating discrete data with continuous data, so it makes sense to me to allow for that. If you don't, it's not as accurate. But remember that both of these are estimates. One might just be a more accurate estimate than the other, but they're still both approximations, because if we wanted to work out the probability of this happening exactly using our binomial distribution, that would be a calculation, remember, that we don't want to do. But what it would look like is the probability of getting exactly 60 sixes. So that would be, what, 480, choose 60, 1/6 to the power of 60, 5/6 to the power of 420, plus, and then we'd have another term for 480, choose 59, and we'd put that, there'd be 60 terms here. No, 61 terms. Would there be? 61 terms, everything from 1 to 60 plus a 0 as well. 61 terms, so we clearly don't want to do it that way and get it exact. Both of these are estimates. One is perhaps a mathematically nicer estimate because it allows for a potential problem with the discrete data being approximated by continuous data. But it's important to note that neither of them is the exact answer. Now let's look at the method that we're learning today using proportions, so we can compare that. Let's do that in red. Now, if we let the proportion equal all of the things that could happen divided by the number of things that there are, then we can say that the expected value of that proportion is just going to be p, and in this case that's going to be the chance of getting 6, so it's 1/6. And we can say that the standard deviation of that proportion, we had a formula for that, it was PQ over N inside the square root, which in this case is 1/6 times 5/6 over 480 with that square root sign going over the entire thing. Okay, for this I get a value of 0.017 or so, roughly. Let's save that as B in the calculator. Now, as we think about what our expected proportion might be and what the standard deviation of that is, if we want to find the probability that the proportion of heads that we get is less than or equal to 1/8, can you see how we're asking the question a different way? We're saying, what is the chance that the probability is of getting a certain thing is a certain thing? So we're finding a probability of a probability. Now, that might hurt your head a little bit, but the method is the same. Effectively, we want to convert that to a z-score and say, let's leave this behind and let's convert it to z. Now, how do we find z-scores? We say how far is something above or below the mean and how many standard deviations is that? So how much is 1/8 smaller than 1/6? Well, let's do 1/6 minus 1/8 to find out. So we get that, 1/24th, and then we need to divide that by the standard deviations to see how many standard deviations 1/24th actually is. So let's divide it by what we saved as b in our calculator, and we're going to get 2.45. But don't forget that this is a negative z-score because we are below the mean. 1/8 is smaller than 1/6. Now, what you'll notice is it's exactly the same as the calculation that we got here. So we're going to get 1 minus 0.9929, because looking this up, I'm going to get the exact same result. And using this method that we're learning today with proportions actually gives us the same result as using the method from the last exercise without any continuity correction. So to my way of thinking, this method is a little bit flawed because it doesn't take into account the fact that we're using discrete data and approximating with continuous data. And it also highlights the fact that perhaps it's not such a big deal whether we use this correction factor or not, if we're going to then, in our syllabus, be using this method as well, because this method is effectively giving us the same answer as we get using this method with no correction. Does that make sense? Now, this is a little confusing. Which method should you use? Use the one that makes sense to you. And it's quite likely that in the HSC, questions that are done either way will be marked correct if your working makes sense with your answer. So I would recommend doing them a couple of different ways. Questions that allow you to work this way, if it makes more sense to you, go for it. And whether you use the continuity correction or not, you're going to find that in your textbook, if they're asking you to do it this way, then probably doing it without the correction is going to be what's in the back of the book. And that's a little confusing because in the last exercise we were doing it this way. So apologies for the confusion with the methods. The thing to remember is that all three of these are approximations. So at the end of the day, we need to sort of round off a little bit and say, look, these things are all very unlikely. I mean, what are the chances here? This is 0.7%, so it's less than 1% chance of it happening. So, I mean, by rights, you could potentially round all of these and just say, look, it's less than 1%. And that way, it's not really going to matter which method you've used.